Hi. In the previous video, we've described how this process of finding maximum and minimum, of course relative, is done using the derivative. But we were doing it in a very general setting, using only graphical interpretation. Now, let's combine what we learned before. So, how to calculate derivatives with the graphical interpretation. And look, we're going to do it using two cases where finding maximum and minimum is extremely trivial. Because we know very well how those functions look like, how they are behaving, so we can simply just make sure that the procedure we're going to use works. Okay, so let's start with a function that we know very, very well, which is the quadratic function y equals x squared. Look, this function we know very, very well. Looks like this. So, here we've got y equals x squared, and we clearly see that this function looks like a valley, and it has a minimum at point 0. Now, let's see if we're going to get actually this outcome by calculating derivative. Now, look, derivative of this function, let's denote it as y prime, is simply equal to 2x, right? Now, it's really, really easy to also draw this function on a graph. So, look, now, what I'm drawing over here is a linear function to x. Y equals to x, but of course here it's y prime. Okay, and this function is upward sloping and it's going through the origin. Okay, now let's see what do we get from the derivative and how does this derivative describing our function. Okay, look, first we see over here that the function is downward sloping. So as we are moving on axis to the left, function is going down lower and lower and lower. And what do we see over here? Look, to the left of 0, value of the derivative is negative. And this makes perfect sense. We said, remember, this is the key thing to the entire process over here. Derivative measures the slope of the function at a given point. So look, if derivative is negative, function should be downward sloping. Now, what is happening to the right of the point 0? Look, here we see that the function is increasing. It's taking bigger and bigger values. And what can we say about the derivative? Look, derivative over here is positive. So finally, we can ask the question, what is happening in the middle? Look, we said that at this particular point, the slope of the function is equal to 0. What is the value of derivative at this point? It is exactly 0. And look, it all makes perfect sense. This is an upward sloping function, right? This is y prime equals 2x, right? So, this function takes lower and lower values with lower and lower x, right? And we see that it's getting closer and closer to 0. That here, we of course have negatively sloped function. Then it turns into 0 when x is 0, and then it goes to be positive, and our original function then is upward sloping. Okay, but let's notice one more thing. Look, here you see x squared is very, very steep, but it's getting flatter and flatter and flatter and flatter and flatter. And what is happening over here? Look, here, values of the derivative are very big in absolute terms, which means they are, for lack of a better term, very, very negative. You know, they take very big negative values. But then, the value of the derivative is getting smaller and smaller and smaller and closer to 0. And at the same time, this function is getting flatter and flatter and flatter. Then it reaches 0. What happens next? Look, here we see that actually this function starts being relatively flat, and it's becoming steeper and steeper and steeper and steeper and steeper. And what is happening with the derivative? At the beginning, the derivative is very small, but it's getting bigger and bigger and bigger and bigger. Another indication of how derivative actually measures the slope of the function. Okay, so now let's consider a case of the simplest possible maximum. I believe that the case of the simplest possible maximum would be negative x squared. Again, we know exactly how this function looks like. And this function looks like this. Right? Okay. So, let's right away, just as we did before, calculate the derivative of this function. Let's denote it as y prime, and we get that this is negative 2x. And now let's put the graph of this function right below. Now, this is again a linear function, but this time it has negative coefficient, which means that it is downwards slope. Okay, and again, let's see what is happening over here. Look, we see that here the parabola is upward sloping. It's getting bigger and bigger and bigger values. And what can we say about the first derivative? Well, the first derivative has positive values. Now, what is happening to the right of 0? Well, the function here is downward sloping. It's taking lower and lower and lower values. What can we say about the derivative? It is negative. Now, we also see that again, when our function here has slope equal to 0, at maximum, value of the derivative is 0. And again, look, we also see that here the function is relatively steep, and it's becoming flatter and flatter and flatter. And what we see here, the values of the derivatives are very big, but they are getting smaller and smaller and closer to 0. Then, when we move right past through 0, the function is downward sloping, but at the beginning is relatively flat, and it's getting steeper and steeper and steeper. What do we see over here? Derivative is very small, but then it gets more and more and more negative. Okay, so look, what have we learned from this? Actually, this confirms everything we said before. Derivative measures slope of the function at a given point. What is more, we see that at the point where derivative is equal to 0, we will have minimum or maximum. But look, we get also an indication of which one is which just by looking at the derivatives. How? Look, because here we know that in order to have minimum, function must be first falling, reaching minimum, and then going up. This is only possible if the derivative changes the sign from negative around 0 to positive, right? So the slope of the function is changing from negative to positive right after 0. And if we want to have maximum, then the function must be first increasing, reaching maximum, and then starts to fall. So derivative first must be positive, then it must be 0, and right after 0, it must be negative. Okay, and look, again, that would be enough for us to decide, but actually this is not very convenient, because like always calculating, checking whether the function changes the sign from one to the other might be troublesome. Especially that now we are just dealing with very simple case, but of course we might have cases that are far more complex. So actually what we can do this time is to calculate derivative of the derivative. And this is what we're going to do here. We're going to calculate second derivative. Look, in this case, let's denote it by y-b's, which is equal to just 2. So if I want to draw this function over here, how will it look? Look, this is a constant function that takes only one value, 2. Okay, now let's for a second forget that we even have this. Let's just say that we are only discussing this function, which is a derivative of this function. So what does it do? This function actually measures the slope of this function. And look, the slope is constant over here. But we also see that the derivative here is everywhere positive. What does it mean? It means that this function must be upward sloping. And if it's upward sloping and it's got 0 in the middle, it must be changing values from negative to positive. So look, this means that if we found a point at which derivative is equal to 0, and we also found that the second derivative is positive, which means that first derivative is upward sloping, then in this around this point, the function changes the derivative changes the sign from negative to positive, and by that, this must be a minimum. Now look, we can do exactly the same thing over here. Here, if I calculate the second derivative, it's again extremely easy thing because it's negative 2. And again, I can put it on the graph below. And again, this is a constant function that always takes the same value, negative 2. Okay. And look, what can I say now? Again, for a second we forget about this, and look, this is the first derivative of this function, right? It tells us that it's always negative, right? So what does it mean for this function? If this is always negative, it means that this function is downward sloping. If it's downward sloping and it has a 0 in the middle, it means it must be changing sign from positive to negative. And again, this indicates that this function is first growing, reaching maximum, and then falling. So this point must be a maximum. Okay, so look, what have we learned from this example? New slide. Look, we know that in this case we've got that first derivative over here is negative, then at this point over here first derivative is equal to 0, and to the right of this point derivative is positive. Okay, so what does it mean? It means that function here, so y is decreasing over here. Here, y takes lowest value around this location, because remember, we are talking about relative or local minimum and maximum. And then what is happening right after this point is that y is increasing. And look, we get information also from the second derivative. Because what is second derivative telling us? Second derivative everywhere in here is negative. And if second derivative is negative, we know that first derivative has 0 in the middle. It means that the function, the derivative must be changing sign from negative to positive, which assures us, of course it's positive. And it assures us that we will have upward sloping derivative, which means we have minimum. Over here, we've got the opposite situation. Here, we've got first derivative to the left of 0, that is positive, function is upward sloping. Then, in the middle, we've got first derivative that is equal to 0, and then right after, first derivative is negative. So, what do we learn from this? Y at the beginning must be increasing, then in the middle we've got y maximum, and then y is decreasing. And this actually is confirmed by the fact that the second derivative is lower than 0, which indicates that the first derivative is downward sloping. But look, if we've got all this information, maybe we can learn even more about this function. What do I mean by that? Look, let's go back to our graph and something that I was mentioning earlier. Look, here we see that the derivative is upward sloping. It has 0 in the middle. But what is this telling us about the general shape of the function? Look, here we see that derivative is very negative, and then, which means that the slope of this function must be not only negative, but very steep. And then it gets closer and closer and closer to 0, and what happens then is that the function is getting flatter and flatter and flatter. It reaches minimum, and then it starts to become positive. But it's becoming more and more and more and more and more positive. What does it imply for our function? That it's increasing, but it's increasing faster and faster and faster and faster, which means that it gets steeper and steeper and steeper and steeper. So, this is another piece of very useful information. But what do we get from this? Here, look, here we are actually getting very similar information. At the beginning, derivative is very big and the function is very steep. But it's, as you see, as derivative gets smaller and smaller and closer to 0, the function is still increasing, but it's increasing slower and slower and slower and slower. So it's getting less and less and less and less steep. Then, when we move beyond 0, what happens is that derivative here at the beginning is negative, but just a little, and then it becomes more and more and more negative. And as this happens, the function is becoming more and more steep, but of course with negative slope. Now, this is the information that we actually learned from first derivative. But maybe this information is also sometimes somehow encoded in the second derivative. And look, it is. Because, look, if first derivative over here cuts through 0, right? And the second derivative is positive, this means that the slope of the first derivative is increasing. If the slope of the first derivative is increasing, this means that the function is getting steeper and steeper and steeper. So look, here we actually saw that function was very steep but with negative slope. But look, as we have positive second derivative, we must have upward sloping first derivative. So as x is getting bigger, we see that this function is declining, but it's declining slower and slower and slower. It reaches 0, and then it starts to increase, and it increases faster and faster and faster. And the same is over here. We remember that second derivative is telling us that the first derivative is downward sloping. What does it imply? It implies that this function at the beginning is increasing, but it's increasing slower and slower and slower and slower. It reaches maximum, but then it starts to fall, and it's falling faster and faster and faster and faster. Okay, so in this case, we can say that the sign of the second derivative will tell us whether we will have a shape like a valley or shape like a hill, or as I prefer to call it, like a cave. So look, every time when we have a situation when second derivative is positive, the function will look like a smiley face. Every time when second derivative is negative, the function will look like a frowny face. But we can also think about it as a hill, or we can think about it as a cave. Imagine that here it's all dark, and this is a cave. Why do I want you to think about it as a cave? Because this type of shape that you see over here is a shape that we call concave. And look, this is a very good mnemonic device to remember it. Because when do we have a concave shape? When it does look like a cave. On the other hand, if we have this type of shape, we call it convex. Why does we call it convex? Because it doesn't look like a cave. Now that we know it, we can actually get a little bit deeper into the relationship between the first and the second derivative. Because look, of course, we can have minimum only at the bottom of the valley. So the shape that gives us a bottom of the valley must look always like this. And look, it turns out, as you see over here, that this convex shape is always present as long as the second derivative is positive. Now, the convex shape, the concave shape that we see over here, is the only one that can produce a maximum. And this concave shape can only be produced with the second derivative being lower than 0. And look, I know that I explained it once, but let me explain it again. Look, second derivative is the first derivative of the first derivative, right? Okay, not very pleasant to hear, but I hope it makes sense in your head. If second derivative is negative, it means that first is negatively sloped, which means that the function, if it has 0 in the middle, is at the beginning very positive. So it's positive in big values, but it gets smaller and smaller and smaller. This measures the slope of the function, which means the slope of the function is steep, but it's getting flatter and flatter and flatter. It reaches maximum, and then again, because second derivative assured us that this must be negatively sloped, it's going to become negative and more negative, and as a result, it will be falling faster and faster and faster. Over here, positive second derivative assures us that first derivative is upward sloping, which means that at the beginning function is characterized by very negative first derivative, which means it's falling very fast. But as derivative gets smaller, it starts to fall slower and slower and slower. Then we reach minimum, and then after this point, it starts when first derivative becomes positive, it starts to increase faster and faster and faster. So look, out of this, we can get even more precise information. Because look, here we can obtain two different shapes. Look, let me just do one more thing before we go further. I was using y prime because it's, let's just say, very convenient. But what we should write over here is probably f of x. With prime, of course. Right? And I'm going to move to this because this is more consistent with what we're going to be using later. But look, the meaning everywhere stays the same. Because here we simply have first derivative. And here, instead of y(b)s, I'm going to write, I already had two primes, this, and of course here, f(b)s of x. Okay, and look, out of this, we can get that we will have, if we have a specific combination of first and second derivative, we will get one of the four types of shape. Because, look, if we've got first derivative that is negative and a second derivative that is positive, what do we get out of this? Look, we see that the first derivative is negative, indicating that the function is downward sloping. But look, second derivative is positive, indicating that the slope of first derivative is getting higher and higher, that the first derivative, slope of the first derivative is positive, which means that the values of the first derivative are getting higher and higher and higher. So every time when we will have the combination of these two, the shape we're going to get is this, and we're going to call it decreasing convex, I'm sorry. doesn't definitely look like a cave. Okay, then, if on the other hand, first derivative is positive and second derivative is also positive, what does this imply? It means that function is upward sloping, right? And the first derivative is upward sloping, which means that it's getting higher and higher in values. This means that our function is increasing faster and faster. So in this case, we get a shape that we call increasing convex. Okay, so, but of course, now we've just dealt with convex functions. Let's move to concave. If first derivative is bigger than 0 and second derivative is smaller than 0, what does this imply? Look, function must be increasing, but the value of the first derivative is getting smaller because the first derivative is downward sloping. So the function is increasing, but it's increasing slower and slower. So this shape we're going to call increasing concave, which of course is like a part of a cave. Now, if now we will have f prime of x negative and f piece of x negative, what should we expect? Well, the function is has negative slope because first derivative is negative, and because the second derivative is also negative, it means that the value of the derivative is decreasing. So what type of shape are we going to have now? Shape where the function is decreasing and it's decreasing faster and faster. We of course call it decreasing concave. Okay, and of course, I hope at this moment you remember that in between increasing concave and decreasing concave, we must have maximum, while between decreasing convex and increasing convex, we have minimum. Okay, so look, let's say a little bit more about first and the relationship between second derivative and function. Look, first derivative measures the slope of the function, right? So this is pretty easy. But what does second derivative measure? Look, if second derivative actually also measures the slope, but it measures the slope of the first derivative. Okay, so let's go maybe step by step. Okay, if we have that at some point f of x0, derivative f prime of x, f prime of x0 is bigger than 0, and if first derivative x0 is smaller than 0, then we get that at this point f of x at x0 is increasing and in the second case, right, when it's negative, f of x0 is decreasing. Okay, that was straightforward. But what about the two situations when we have second derivative that is positive or against second derivative that is negative? What does this imply implies for our function? Look, let's get back to this example again. Look, because here second derivative was positive, we knew that the first derivative is upward sloping. And look, if the function is upward sloping, it means it goes from lower values to bigger values. Which means that if f prime of x0 is bigger than 0, it means that f prime at x0 must be increasing. And, of course, here, if second derivative is negative, it means that f prime of x0 must be decreasing. But now, if we know this, what does it mean for the original function? Well, okay, look, here we've got that we always remember, derivative measures the slope of the function at a given point, right? So, if second derivative is positive, this means that first derivative is increasing. But if first derivative is increasing, it means that the slope of our original function, f of x0, is increasing. Which means that we can have two cases here, right? Either the function is falling, but it's falling slower and slower, or it is increasing and it's increasing faster and faster. On the other hand, if now we've got that second derivative is negative, this means that the slope of the first derivative is that the first derivative is going down. What does it mean? Which means that the first derivative is going down. What does it mean? It means that the slope, maybe not of, let's write it as at f of x0 is decreasing. So, how can we have a situation like that? If the function is increasing, it means that it increases slower and slower, but if it decreases faster and faster. Okay, now, so if the first derivative relates to the slope of the function, then second derivative relates to its acceleration. And look, this means that if second derivative is positive, it means that first derivative is increasing and the slope of the function is increasing, which means that this function has positive acceleration. And again, over here, if second derivative is negative, it means that the first derivative is decreasing, and if the first derivative is decreasing, the slope of the function is decreasing, which means we've got negative acceleration. Okay, so our function will be either increasing slower and slower or decreasing faster and faster. Well, very well. So, look, we are very, very close to finally put down a formal test that will allow us to find maximum and minimum of a function. But before we go to it, let's consider one more specific case that may illustrate the necessity of using the specific conditions that I'm going to introduce to you in a couple minutes. Okay, so now let's consider again a function that we know very well. Y equals x cubed. How does this function look like? Well, this function looks like that. Okay, and look, what do we see? Look, we see that this function is always increasing. It is always, it is concave to the left of 0, and it is convex to the right of 0. Okay, let's see if this is what we're gonna get if we calculate derivatives. Okay, so now y prime, so f prime of x, is equal to 3x squared. And look, 3x squared is another quadratic function, right? So, just, if I want to draw this function, I'm going to draw it in the following way. And of course here I have y prime. And look, what do I see over here? Here, our function is increasing, and the value of the derivative is positive. But to the right of point 0, function is increasing, but actually it's increasing faster and faster. Here was increasing slower and slower. Here, values of the derivative are positive. And now, let's see this example in more detail. Look, here we see that the derivative is positive, but it's getting smaller and smaller and smaller. And we see that the function is increasing, but at the decreasing rate, right? So it's getting flatter and flatter and flatter. It reaches 0, but then, right next to it, it starts to increase, and we see that the derivative is getting bigger and bigger and bigger. And the function starts to increase faster and faster and faster. Okay. So, but in this case we might have a problem, right? Because using first derivative test only, we could get that this point is a candidate for maximum. But let's see what happens if we calculate here the second derivative. And look, second derivative here is 6x. So if I want to draw the second derivative, I'm drawing a function like this. And again, we now see that the second derivative at our point of where we have maximum, or where we could think that we have maximum or minimum, has actually derivative that is equal, second derivative equal to exactly 0. And look, this is actually what distinguishes this case from those two previous cases. Look, if we now know, of course, if we would only use first derivative test, we would only know if the point is a candidate for minimum, for maximum, or for what we said is called inflection point. And look, now, this is the same inflection point I've been telling you about in the previous video, but now we can actually say it in a more professional way. Look, inflection point is a point where the curvature of the function is changing from concave to convex, or if we would have a function y equals negative x cubed, which would look like this, then we would have the opposite situation. It would be changing from convex to concave. So this type of point we're going to call inflection point. And look, this point will be characterized by the fact that derivative, first derivative, is either around this point always positive or always negative. Right? Because for this function, look, the second derivative would look negative 3x squared. It would look like this. And the third derivative, the second derivative would look negative 6x like this. So look, over here, if we have a situation when first derivative around some 0 point, critical point, is always positive, but the second derivative is 0, this means that we have inflection point. And we need to take this into consideration when we devise a test for relative maximum or relative minimum. And let me now specify this test for you. In a way that is very consistent and easy to apply when we deal with the minimization and maximization problems. Okay, so let's call this conditions for relative maximum, maxima, or minima. And look, this test has two stages. First stage is called first order condition, because we are using first order derivatives. For short, we usually use FOC, first order condition. And look, this condition is so-called necessary condition. Why is it called necessary condition? Because look, if this condition is not met, then at the given point, we definitely not going to have either minimum or maximum. And what is this first condition test? Well, it's very simple. Look, if we've got a function y equals f of x, then first order condition is extremely simple. We calculate first derivative dy dx, or we can call it f prime of x, and we equalize it with 0, right? We're looking for points where slope of the function is equal to 0. Now, but of course we saw that this type of point we will have when we have maximum, minimum, or inflection point. So then we need to go to second order condition. And second order condition, or SOC for short, actually has two versions. Okay, let me just get some colors and let me start explaining. Okay, first I'm going to show you the necessary version, and then I'm going to show you the sufficient version. And look, in all our applications in this class, we will be using only sufficient version. Okay, but let me specify necessary, and okay, different color. Necessary goes like this, that if second derivative if the second derivative is at some point, no, it's better to use this x0, at a given point x0 is lower or equal to 0, we've got maximum. But if second derivative is bigger or equal to 0, we've got minimum. Okay, and now, actually necessary condition is more complex. I will show you the difference in a few minutes. Let me now just show you sufficient version. And this is the version I want you to use in our class. So, sufficient says that d squared y dx squared equal to fb of x0. If it's smaller than 0, this is definitely a maximum. If d squared y dx squared, so if the second derivative at a given point is lower than bigger than 0, this means that we've got minimum. Okay, why do we need to distinguish between those two cases? I'm going to illustrate you this with the example of a maximum, because example for minimum would be the same. Okay, look. When we were considering maximum and minimum before, I was drawing this maximum or minimum to you. Maximum, let's take to maximum like this, right? So we had one point, one particular point on which slope of the function is equal to exactly 0. But there is a second possibility that we haven't included. Look, what if our function would look like that? Now, the difference here is that, look, if second order condition in sufficient form is fulfilled, we can be 100% sure that we will either have maximum like here or minimum. But look, in this case over here, each point over here is a maximum in this neighborhood, right? So, if each of these points is a relative maximum, then this sufficient condition would be too strong to recognize that these points, or all these points, are actually maximum points. This is why in those cases we can use necessary version, which of course makes things a little bit more problematic. But as I told you, I wanted to explain the difference, why the first condition is called necessary, and then we're going to switch to sufficient. And look, because in our considerations, we will be considering either caves, or hills, or frowny faces, or valleys, or smiley faces. We're not going to consider cases like this. I just want you to know that when we have a case like this, then necessary condition is better. And remember that also, if sufficient condition is fulfilled, then definitely necessary condition is fulfilled. You know, because what does it mean necessary? That something needs to be fulfilled before we proceed. Sufficient means we have enough, we don't need to do anything else. And sufficient condition establishes either maximum or minimum right away. Okay, thank you for your attention. In the next video, I'm going to show you examples. Because now we get a lot of theory, but as you will see in those examples, using derivatives to drawing functions, finding maximum or minimum, is way easier than maybe it might seem from everything I've been saying thus far.